In physics, a field is a physical quantity that has a value for each point in space and time. For example, on a weather map, the surface wind velocity is described by assigning a vector to each point on a map. Each vector represents the speed and direction of the movement of air at that point. As another example, an electric field can be thought of as a condition in space, emanating from an electric charge and extending throughout the whole of space. When a test electric charge is placed in this electric field, the particle accelerates due to a force. Physicists have found the notion of a field to be of such practical utility for the analysis of forces that they have come to think of a force as due to a field. In the modern framework of the quantum theory of fields, even without referring to a test particle, a field occupies space, contains energy, and its presence eliminates a true vacuum. This led physicists to consider electromagnetic fields to be a physical entity, making the field concept a supporting paradigm of the edifice of modern physics. The fact that the electromagnetic field can possess momentum and energy makes it very real. A particle makes a field, and a field acts on another particle, and the field has such familiar properties as energy content and momentum, just as particles can have. In practice, the strength of most fields has been found to diminish with distance to the point of being undetectable. For instance, the strength of many relevant classical fields, such as the gravitational field in Newton's theory of gravity or the electrostatic field in classical electromagnetism, is inversely proportional to the square of the distance from the source. One consequence is that the Earth's gravitational field quickly becomes undetectable on cosmic scales. A field can be classified as a scalar field, a vector field, a spinor field or a tensor field according to whether the represented physical quantity is a scalar, a vector, a spinor or a tensor, respectively. A field has a unique tensorial character in every point where it is defined, i.e., a field cannot be a scalar field somewhere and a vector field somewhere else. For example, the Newtonian gravitational field is a vector field. Specifying its value at a point in space-time requires three numbers, the components of the gravitational field vector at that point. Moreover, within each category, a field can be either a classical field or a quantum field, depending on whether it is characterized by numbers or quantum operators respectively. In fact, in this theory an equivalent representation of field is a field particle, namely a boson. History. To Isaac Newton, his law of universal gravitation simply expressed the gravitational force that acted between any pair of massive objects. When looking at the motion of many bodies all interacting with each other, such as the planets in the solar system, dealing with the force between each pair of bodies separately rapidly becomes computationally inconvenient. In the 18th century, a new quantity was devised to simplify the bookkeeping of all these gravitational forces. This quantity, the gravitational field, gave at each point in space the total gravitational force which would be felt by an object with unit mass at that point. This did not change the physics in any way. It did not matter if you calculated all the gravitational forces on an object individually and then added them together, or if you first added all the contributions together as a gravitational field and then applied it to an object. The development of the independent concept of a field truly began in the 19th century with the development of the theory of electromagnetism. In the early stages, André-Marie Ampère and Charles-Augustin de Coulomb could manage with Newton-style laws that expressed the forces between pairs of electric charges or electric currents. However, it became much more natural to take the field approach and express these laws in terms of electric and magnetic fields. In 1849, Michael Faraday became the first to coin the term field. The independent nature of the field became more apparent with James Clerk Maxwell's discovery that waves in these fields propagated at a finite speed. Consequently, the forces on charges and currents no longer just depended on the positions and velocities of other charges and currents at the same time, but also on the positions and velocities in the past. Maxwell, at first, did not adopt the modern concept of a field as fundamental quantity that could independently exist. Instead, he supposed that the electromagnetic field expressed the deformation of some underlying medium, the luminiferous ether, much like the tension in a rubber membrane. Despite much effort, no experimental evidence of such an effect was ever found. The situation was resolved by the introduction of the special theory of relativity by Albert Einstein in 1905. This theory changed the way the viewpoints of moving observers should be related to each other in such a way that velocity of electromagnetic waves, in Maxwell's theory, would be the same for all observers, by doing away with the need for a background medium. This development opened the way for physicists to start thinking about fields as truly independent entities. In the late 1920s, the new rules of quantum mechanics were first applied to the electromagnetic fields. In 1927, Paul Dirac used quantum fields to successfully explain how the decay of an atom to lower quantum state lead to the spontaneous emission of a photon, the quantum of the electromagnetic field. This was soon followed by the realization that all particles, including electrons and protons, could be understood as the quanta of some quantum field, elevating fields to the status of the most fundamental objects in nature. That said, John Wheeler and Richard Feynman seriously considered Newton's pre-field concept of action at a distance. Classical fields. There are several examples of classical fields. Classical field theories remain useful wherever quantum properties do not arise, and can be active areas of research. Elasticity of materials, fluid dynamics, and Maxwell's equations are cases in point. Some of the simplest physical fields are vector force fields. Historically, the first time that fields were taken seriously was with Faraday's lines of force when describing the electric field. The gravitational field was then similarly described. Newtonian gravitation, a classical field theory describing gravity as Newtonian gravitation, which describes the gravitational force as a mutual interaction between two masses. Any body with mass m is associated with a gravitational field G, which describes its influence on other bodies with mass. The gravitational field of m at a point r in space corresponds to the ratio between force F that m exerts on a small or negligible test mass m, located at r, and the test mass itself. Stipulating that m is much smaller than m ensures that the presence of m has a negligible influence on the behavior of m. According to Newton's law of universal gravitation, F is given by where as a unit vector lying along the line joining m and pointing from m to m. Therefore, the gravitational field of m is the experimental observation that inertial mass and gravitational mass are equal to an unprecedented level of accuracy leads to the identity that gravitational field strength is identical to the acceleration experienced by a particle. This is the starting point of the equivalence principle, which leads to general relativity. Because the gravitational force F is conservative, the gravitational field G can be rewritten in terms of the gradient of a scalar function. The gravitational potential phi. Electromagnetism. Michael Faraday first realized the importance of a field as a physical quantity during his investigations into magnetism. He realized that electric and magnetic fields are not only fields of force which dictate the motion of particles, but also have an independent physical reality because they carry energy. These ideas eventually led to the creation, by James Clerk Maxwell, of the first unified field theory in physics with the introduction of equations for the electromagnetic field. The modern version of these equations is called Maxwell's equations. Electrostatics. A charged test particle with charge Q experiences a force F based solely on its charge. We can similarly describe the electric field E so that F equals QE. Using this, and Coulomb's law tells us that the electric field due to a single charged particle as the electric field is conservative, and hence can be described by a scalar potential. Magnetostatics: a steady current I flowing along a path will exert a force on nearby moving charged particles that is quantitatively different from the electric field force described above. The force exerted by I on a nearby charge q with velocity v is where B is the magnetic field, which is determined from I by the Biot-Savart law. The magnetic field is not conservative in general, and hence cannot usually be written in terms of a scalar potential. However, it can be written in terms of a vector potential. Electrodynamics in general, in the presence of both a charge density ρ and current density J, there will be both an electric and a magnetic field, and both will vary in time. They are determined by Maxwell's equations, a set of differential equations which directly relate E and B to ρ and J. Alternatively, one can describe the system in terms of its scalar and vector potentials V and A. A set of integral equations known as retarded potentials allow one to calculate V and A from ρ and J, and from there the electric and magnetic fields are determined via the relations at the end of the 19th century. The electromagnetic field was understood as a collection of two vector fields in space. Nowadays, one recognizes this as a single antisymmetric second-rank tensor field in spacetime. Gravitation in general relativity. Einstein's theory of gravity, called general relativity, is another example of a field theory. Here the principal field is the metric tensor, a symmetric second-rank tensor field in spacetime. This replaces Newton's law of universal gravitation. Waves as fields. Waves can be constructed as physical fields due to their finite propagation speed and causal nature when a simplified physical model of an isolated closed system is set. They are also subject to the inverse square law. For electromagnetic waves, there are optical fields, and terms such as near and far field limits for diffraction. In practice, though the field theories of optics are superseded by the electromagnetic field theory of Maxwell, quantum fields, it is now believed that quantum mechanics should underlie all physical phenomena, so that a classical field theory should, at least in principle, permit a recasting in quantum mechanical terms. Success yields the corresponding quantum field theory. For example, quantizing classical electrodynamics gives quantum electrodynamics. Quantum electrodynamics is arguably the most successful scientific theory. Experimental data confirm its predictions to a higher precision than any other theory. The two other fundamental quantum field theories are quantum chromodynamics and the electroweak theory. In quantum chromodynamics, the color field lines are coupled at short distances by gluons, which are polarized by the field and line up with it. This effect increases within a short distance, making the color force increase within a short distance, confining the quarks within hadrons. As the field lines are pulled together tightly by gluons, they do not bow outwards as much as an electric field between electric charges. These three quantum field theories can all be derived as special cases of the so-called standard model of particle physics. General relativity, the Einsteinian field theory of gravity, has yet to be successfully quantized. However, an extension, thermal field theory, deals with quantum field theory at finite temperatures, something seldom considered in quantum field theory. In BRST theory, one deals with odd fields, e.g., Faddeev Popov ghosts. There are different descriptions of odd classical fields both on graded manifolds and supermanifolds. As above with classical fields, it is possible to approach their quantum counterparts from a purely mathematical view using similar techniques as before. The equations governing the quantum fields are in fact PDEs. Thus one can speak of Yang-Mills, Dirac, Klein-Gordon and Schrödinger fields as being solutions to their respective equations. A possible problem is that these RWEs can deal with complicated mathematical objects with exotic algebraic properties, but these in theory can still be subjected to analytical methods given appropriate mathematical generalization.